Hello everyone, welcome to the GRAMOLY channel. Today we'll be solving problem 3 from INChO 2015. This problem is based upon organic reaction intermediates. So first of all we'll read the problem and then do the problems. It says many organic reactions proceed through intermediates such as carbocations, carbanions, carbon radicals, carbenes, etc. The structure and stability are crucial factors that determine the reaction mechanism. Well, an intermediate forms in the reaction and then it decides the stability. So just highlighting that. And then it says the formation of cation, the stability of the carbocation determines the rate of the reaction. And then there's given name of Hammond postulate is an important tool to discuss transition state. Let's solve the first problem. It's based upon the rate of addition of Hi. So basically they're asking the electrophilic addition in alkenes. Well, let's say we have the first one and then we add Hi to it. So this double bond will attack on this hydrogen and I will leave. Then it forms a carbocation. This is a 3-degree carbocation. So it will have more stability than the 2-degree one and the 1-degree one. And in the second one we have this compound and Hi. So the reaction follows for the electrophilic addition to alkenes, and this will form a 2-degree carbocation. And now for the last one, we have with the pH attached, that is the phenyl group. And this forms a 2-degree cation as well. Let's see how it forms. It forms like this. But this carbocation will be in resonance with this pH. So we can say that this will be most stable because it forms resonating structures with phenyl group, and hence it forms hence it provides more stability to this alkene. Hence we can say this is the third one, this is the second, and this is the first. So the stability order would be 3 is greater than 1 is greater than 2, and we can say this is because of the degree of carbocation, and this is because of resonance. So we solve the first problem and hence we can write the answer. 3 is greater than 1 is greater than 2. And now we go to the next problem, that is the rearrangements of carbocations are very common. Yeah, that's actually true, because if a carbocation forms at suppose 3-degree or suppose 2-degree, then it will prefer to go to a 3-degree carbocation to get more stability. The group that migrates, so it's basically based upon migratory aptitude. We need to check which group will migrate and which group will stay on its position. Let's just highlight this and let me add a page. Okay. It asks for this compound. And then they say they have added H plus to it in non-aqueous medium. So this so the oxygen will take this H plus, and basically this is the protonation step, and this will form like this: pH CH3 OH2 plus, or to see it in more detail we can write like this: like a curvy arrow, and it forms a bond with hydrogen, and there's a formal charge on H, and this is basically a good leaving group. This will leave, and there would be a formation of carbocation at this carbon. Let's see how it forms: pH CH3 and a carbocation. And now it says that in the problem, compound A on treatment with a Bronsted acid gives compound C. In the reaction, B is an intermediate formed through a rearrangement. And they also said that the group that migrates is generally the one that is electron rich, and we know that pH is more electron rich than CH3, so the group that will migrate is pH3. So let's migrate it with a curvy S-type arrow, and this will form like this: CH3, and the carbocation would be at this place now. And now this would be our stable intermediate, that is the B. So we can draw this, and this would be our answer for B. And now they have said in the reaction B is an intermediate, and so we need to form the C product now. So this is our product, that is B. Well, this was actually pH, sorry about that. And now this hydrogen will give its electron to form a double bond and neutralize the positive charge. Let's just draw it with some other color, and this will form the product C, that is the CH3, and hence this will be our answer for C part. So we solved the first two problems and we got the answers. So let's move to the next problem, that is the 3.3. Okay, compound D on reaction with limited quantity of chlorine. Well, there isn't excess quantity of chlorine. Limited quantity of chlorine in the presence of UV light under ambient conditions give a mixture of products. The major product is, well, what we need to do here is monochlorination reaction. Since there isn't excess chlorine and it's in the presence of UV light, so it's monochlorination, and this also proceeds by the formation of a carbocation, and then we form the product. Now let's see the positions carbocation can form. This is the first position, these two are the same, so we won't count that. This is the second, this is third, this is fourth, this is fifth, and it can also form here, here, and all these points. So a carbocation is more stable at 3 degree carbon, and that is more stable than the 2 degree one, and that is more stable than 1 degree. So the most favorable points are 4th, 3 and 2. Let's see which one would be more stable. There would be a formation of radical, because we are adding chlorine, so it would basically form a carbon radical here. And we see that this has, so now we will have to compare the alpha hydrogens this carbon radical has. So here it is 3, here 1, and here it is 2. So this carbon has 6 alpha H. Okay, let's add another page and draw the molecule. We got 3 points, that is the first, second and third. So for carbon 1, we'll have 6 alpha H. For carbon 2, we'll have 1 here, 1 here and 2 here. So for carbon 2, we have 4 alpha hydrogens, and for carbon 3, we'll have, so this will have 3, here 3, and here it would have 1 alpha H. So in total we have 7 alpha H. So this would be most stable, and hence the most stable compound will look like this. And the Cl would give one more electron and form bond with it. So it would form this major product, and this is our answer for E part, from D to E. Let's move to the next problem, that is, use the following compounds to answer the questions. We have 8 molecules or 8 compounds, and we need to tell aromatic compounds as they are drawn. So we'll have to check from the way they are drawn. This is the first structure. Here B has vacant p orbitals, so it can have resonance among them, and hence it will be an anti-aromatic compound. This is the tub shaped, it's also known as the cot, and it's in tub shaped, not planar, so it will be non-aromatic. And now here we'll have to count the number of electrons. So see here it has 2, and then here it also has 2, and now we'll count the, here it has 2 because only one of them can resonate with the another. So 1 2 3 4 5 6 7 8 9. It has 9 resonating bonds, so 9 times 2, that is 18, which is 4 times 4 plus 2. So third should be aromatic. Let's see the fourth one. It has 3 here and 3 here, so total 6 pi electrons, actually 6 pi bonds which are in resonance, so 12 pi electrons, and which is 4n pi, multiple of 4n pi, so it would be anti-aromatic. Now let's see this one. This is actually an interesting one. it has a positive charge here, but it forms 4 bonds here, and hence it is the formal charge, and it doesn't have any p or empty p orbital. So this is sp3 atom, so it won't participate in resonance, and hence this will be non-aromatic. Okay, so here we have this as sp2, which doesn't participate in the resonance, and hence this is an anti-aromatic compound as well. Sorry, it's actually non-aromatic, and because there's no current of electrons, so the current of electrons is not present, and hence it is an non-aromatic compound. Let's see this one. It is sulfur molecule, sulfur element here, and we can see these are localized electrons. So in total we have 6 pi electrons here, so this will be aromatic, and there's an electron current there. Here it is the sp3 atom, which stops the electron current, so there's no complete resonance inside the ring, and hence it will be non-aromatic. Now let's answer the problems. Aromatic compounds as they are drawn. So the aromatic compounds are 3 and 7. So the answer for first will be 3, 7. And anti-aromatic compounds are 1, 4. These are the only 2 which are anti-aromatic, and the rest are non-aromatic. So 2, 5, 6 and 8. And now they have asked another question, that is the non-aromatic as drawn but have resonance structures that are aromatic. So basically they are asking which are quasi-aromatic. Important term to remember. So let's see which is a quasi-aromatic, and we need to check it from the non-aromatic ones. So we'll check from 2, 5, 6 and 8. So let's add a page. We draw, so this molecule cannot get planar. It will always stay in the tub shaped form as it is the most stable form of it. And the fifth one also cannot be quasi-aromatic because it won't release an electron to get the resonance inside the ring. And let's see the sixth one. So here this pi bond will break and it will go towards the oxygen because it is more electronegative, and this will form this structure. And now there's an electron current inside the ring, and this has become quasi-aromatic as the electron can resonate inside the ring. Hence we can say that the compound 6 is quasi-aromatic. And 8 will, okay, let's see the 8th one as well. Here it is 2 pi electron, that is why it is aromatic. So 8th one is this molecule, and if we want to make it aromatic, so it will have to lose 2 H from here and it will form a negative charge. Well, actually, it would form, okay, it doesn't form any structures, but it is the part of question 5 because it can form the conjugate base by releasing the H and forming a negative charge, and thus it will have current of 6 pi electrons, and hence it will be an aromatic conjugate base. So this will be answer for 5th one. So the answer for 4th is 6 and answer for 5th one is 8. And let's see if there is another one which can form an aromatic conjugate base. So 5th one also can form an aromatic conjugate base by having a negative charge at this nitrogen atom. So we can say the 5th one also forms an aromatic conjugate base. Now let's see, 6th question is nor aromatic and pKa around minus 3.8. So basically it's asking pKa is around minus 3.8, so it's highly acidic, and only one that is highly acidic, it can form the aromatic conjugate base, which would be 5. So this should be our answer for 3.4th part, and I think this should be clear how we got the answers. For first, let's review the first three parts, that is the aromatic compounds as they are drawn. So as they are drawn, we have predicted whether they are aromatic, anti-aromatic or non-aromatic, and in the 4th, 5th and 6th part they have asked if they can form aromatic or not, or anti-aromatic. So let's move to the next part, that is the 3.5th part. Okay, well, we have aromatic compounds are difficult to reduce, how the Australian chemist A.J. Birch. So it's basically based upon Birch reduction. Let's see how we do the Birch reduction here. So we can read the para and get the hints. Benzene can be reduced to 1,4-cyclohexadiene. In this reaction, the metal gives an electron. This is an important point for the Birch reduction. This is the Birch reduction to form a radical anion. In this intermediate, the radical center and the anionic center are 1,4 positions. Okay. And here we have the 3-methyl anisole. First of all, let's draw the structures. We have got 3-methyl anisole. This is the structure of anisole. And now we need to do the Birch reduction. It's in the presence of Na and liquid NH3. It is the proton donor. And Na is electron donor to this compound. Hence it forms the it says that can be reduced to 1,4-cyclohexadiene. So the 1,4 positions can be, this can be one of them. Okay, that was 3-methyl, so at the third position it would be third methyl. This is the first, second and third. Sorry. And we can have one another, that is this one, and one another, that is this one. We are not going over the reaction mechanism of Birch reduction, as in the problem it mentions 1,4-cyclohexadiene. So this would be our answer for 3.5 part. Now let's move to the 3.6 part, that is draw the possible structures of G based on the structures of F. So G is formed if we treat it with hot dilute mineral acid. Now we need to treat these compounds, these three, with hot dilute mineral acid. So we can add Hi to them. So this was our answer for 3.5 part. So let's actually encircle them. And we add Hi. Since it is the hot dilute mineral acid, and the work of it is to form alcohol, actually alcohol, but that alcohol won't be much stable because it's more reactive, so it would form ketone if it has the possibility of making ketone by conjugation. Let's see how this proceeds. So it would attack on Hi, form bond with H, and I leaves. So something like this. I leaves and it forms bond with H. It has a formal charge on oxygen atom, and then the I minus. Okay, let's draw it here. Oh, it's the structure is this one. We can expand Me as CH3. So the I minus attacks on the carbon as it is I minus works as a nucleophile to attack on carbon, and hence these electrons are taken by oxygen. So it forms this compound OH, and this would get reduced to ketone as it would be more stable, and this hydrogen would leave. So this would form like this, and this hydrogen would leave at the last step. So we can predict these compounds as simply as O double bond O. This is the first one. The second one is this one. So this does not have the possibility of forming a ketone, although it can with the rearrangement. So we can form a ketone here with the rearrangement, but I don't want to get into that. And in this we can form a ketone like this. So this should be our answer for 3.6. Let's see the 3.7 part, that is with the reaction with Br2. It gave compound H on heating with alcoholic KOH gave I, and G that is actually obtained is not chiral. Okay, the work of Br2 is D. Br2 is added because it's breaking the double bonds on an alkene, and the work of alcoholic KOH is to do dehydrohalogenation. Okay, and the compound that is not chiral is this is chiral. This is the chiral center. This is also chiral, but this is not chiral. So our answer for G would be this. Let's move to H1. We add Br2 to this. It does electrophilic addition reaction, and we have this molecule that's the carbocation would form at this carbon, that is the 3° one, because it would be more stable. And here it is. This is the CH3 and this is Br. So let's talk about the stereochemistry of this compound. This is the Br. It can give its electron to the LUMO of this, to the anti-bonding orbitals of this carbon atom, and form a ring type structure with it. So it can form like this. Suppose it's in the outer plane coming towards the viewer, and CH3 is here. So the only option for Br minus to attack is, so this would neutralize the positive charge there, and Br minus would attack from here, and it would open the ring. So the structure we get is this. Br attacks from the back side, so it would be away from the viewer, and this can be one of the compounds. So this was the stereochemistry of this molecule, but in this question it doesn't mention if we need to find the stereochemistry or not, but let's do without it. So this can be one of them, and BrCH3 and the double bond, and now we need to add QH, so it will dehydrohalogenate the Br, and hence we'll have this molecule. It would take this Br with it, it would form a more stable carbocation, and then this hydrogen will give its electron to this and Br would leave, basically the elimination reaction. And here it is the E1CB reaction, so Br leaves and this double bond is formed with CH3 and Br is here and the ketone there. This is our answer for I part. Let's encircle them. Okay, let's move to 3.9 part, that is E. Vogel is well known for his work on bridged annulenes. Okay, annulenes are large ring compounds containing continuous conjugation. Compound O is one such compound synthesized from naphthalene by the following route. So the route is given here. Compound K adds the equivalence of bromine. Okay, and carbene is a very reactive intermediate here. So we'll have to look about carbene here. In the first step there is Na liquid NH3, so it would do Birch reduction and form the 1,4-cyclohexadiene. So we can write directly the 1,4-cyclohexadiene would be this, not in conjugation. So the answer for our K part would be this. This double bond is in both the benzene, not the benzene rings, but the cyclo. You can say it as this, both the rings. It is common to both the rings. And then we add the carbene. So the carbene will be more stable if it attacks here, as it would get more stability. So it would form an intermediate, that is the cyclopropane, as it is mentioned here. Let's see how it forms. Making it bigger so there isn't any problem. Here's the double bond. It attacks on one of the ends and then it forms bond with this so that it gets stabilized. The charges are stabilized and this formed something like this in the above plane, and the double bonds are there. So this would be our answer for L part, and let's draw it. And for the M part we are adding Br2 in excess, so it would do the electrophilic addition reaction and would break the double bonds. So making it directly Br, 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 and this cyclopropane. And now we add alcoholic KOH, which will work in the dehydrohalogenation and form carbocation. How will this work is that this hydrogen present here would give its electron here, and the Br leaves, so a double bond is formed here. This hydrogen will give its electron and the Br leaves, so a double bond is formed here as well, and it will form a double bond here and a double bond here for the N part. So we can draw N here as so this would be our answer for N, and this will rearrange to give this O molecule. And now we have carbonyl let's move to the next problem, that is carbonyl compounds with acidic hydrogen can exhibit tautomerism and can exist in enol form. Well, it exists mostly in keto form as it is more stable, but it can exist in enol form under some conditions. So we need to find the most stable enol here. First we'll draw the enolate. The enolate which would be more stable is, first of all let's see the mechanism. the H will leave from here and it would have a negative charge, so this will resonate, and a negative charge on O is more stabilized. So this would be our answer for the enolate part. And now for the enol part, we can simply add H to the O minus, as tautomerism is just the resonance and the movement of one atom from one position to another position. So this is the stable enol and this is a stable enolate. Okay, this problem also has a second part, that is draw the structures of the most favorable products obtained from the reactants in the following reactions. So here we have C2H5O minus. It has a tendency of forming an alcohol. One can easily see that if we add an H here, it would form a 1 degree alcohol. So this would take that alcohol from here and it would form this CH2C double bond OCH3, as it had the chance to take an hydrogen from this oxygen and form a stable alcohol, so it did that and we got this product. Similarly here here it is forming the protonation reaction. So what it does is, just this oxygen would take the H from here and it would get reduced, like it can just leave or it would stay in this form. Or what it can do is just take these electrons and form CH3C OH, and this also forms OH, but 2 OH on a carbon atom is not stable, so it would dehydrate and it would form this compound, that is CH3C double bond H, and it would be more stable. Okay, let's move to this 3.11, that is the aza enolates are the nitrogen analogous of enolates. Draw the structures of the aza enolates. So tautomerism can also occur with nitrogen atom here. Let's see how it does. So the hydrogen atom from here would leave and it form a negative charge. This negative charge would resonate and will have a negative charge on nitrogen atom, which would be more stabilized, because a negative charge on nitrogen is more stabilized than a negative charge on carbon, and hence it forms this compound, that is this. So this would be more stable as I enolate. Let's move to the next problem, that is the reactant shown in 3.11 can be prepared by the condensation. Okay, this is the molecule, so we need to prepare this by the condensation. Here we have the secondary amine. If we'll have a secondary amine in the reactant, it will form a tertiary amine. So these two options get eliminated and we need to check from these two. If we take an aldehyde and a primary amine and we just condense it, so we have the chances of forming it. And if we take a ketone it leaves with the H2O and it forms a double. There are two rings, two chains of carbon at carbon. So in this case we have double bond H2NR. This will condense and form an acylolate. So this would be our answer, that is 3. Let's move to this next problem. That is the managed reaction between formaldehyde, secondary amine and a ketone, and the example is given below. And in the next problem it's given that identify the structures of compound P2S in the synthesis of a local anesthetic, that is the titocoin hydrochloride, that is the S. So let's start with the reactions. So basically what happens in the managed reactions, let's just see the mechanism of this. We are given this compound. Let's actually mark this with another color. So this lone pair would attack on this carbonyl group, that is on the carbon, and this electron will move towards oxygen. Well, this attack is on the formaldehyde. So the attack is on the formaldehyde by the nitrogen lone pair, and this electron move towards the oxygen and it forms this intermediate, that is OH. Because in the first step it asks, we have done the protonation, so it would form H2O plus, or basically OH plus, and this would leave. So this forms a alcohol with H, N, H, and now these lone pairs would be given to this carbon atom and this hydroxyl group would leave, basically forming this compound, that is or rather we can say this is CH2 double bond N Me2. And now we have got this product from these reactions. What this can do is, we have got another reactant, that is this one, and now we'll follow the second step, that is of adding OH minus, which will basically trap the acidic H and form this enolate. And these enolates, this negative charge would attack on this carbon and these electrons would be shifted towards nitrogen, forming a negative charge on nitrogen, or its positive charge would get neutralized. Hence, we can say the compound that's formed is this one. This is the CH2 and this is N. So this compound would be formed from the managed reaction. So this is our answer for P. Let's move to the Q part, that is adding a NaBH4, which reduces, so the work of NaBH4 is to reduce ketone or aldehydes. It cannot reduce the carboxylic acids because it doesn't have that reducing nature, to alcohol, to primary or secondary alcohol depending upon ketone or aldehyde. Now we'll proceed from here. So this was our product from the previous reaction. If we add NaBH4, this ketone would get reduced to alcohol. And now we'll have this alcohol. So this would be our answer for Q part. Let's move to the next one, that is the R for the formation of our product. We add NO2 is at the para position of this benzene acyl chloride. Okay, let's draw this. OH, N, and we have added NO2, CO, C double bond, Cl. So this is the carbonyl group here, so it's susceptible to the attack, so the lone pairs of oxygen would attack here and the Cl would leave because it's a good leaving group, and this will form as O, C double bond. We can write it as PH, NH2, NO2 actually. PH represents the phenyl. And this would be our answer for the R part. Let's move to the S part, that is the addition of Sn and HCl. Well, what Sn and HCl does is reducing the nitro group to the amine group. So we can just replace this nitro with NH2, and this would form this compound. In place of Sn and HCl, we can also take Fe and HCl or Zn and HCl. They also show the reducing nature. Okay. In the answer it says the C14H23O2N2HCl. Cl is also present, but in our product it isn't there. So this HCl would also be there in the product, and we just draw with this dot sign so that it is represented in the product. And here we'll end our discussion for this third problem. Hope you like the solutions and the method I discussed in this video. Thank you.